So welcome everyone. Today's speaker is Estel Cardellach. Most of you, well, all of you know her. She's a distinguished researcher here in the Institute, and she's also the lead of the Earth Observation Group. And today she will talk about the HydroGNSS mission. So Estel, go ahead. You can share your screen and start the presentation.
Thank you very much. I will share my screen. I also would like to wish you all Happy New Year. And as Ramon mentioned, I'm going to explain you the HydroGNSS mission. This is a new mission that uses reflectometry of navigation signals to monitor climate parameters. And first of all, this is a seminar to describe this new ISA mission, which is now under implementation, and the materials that I'm going to show have been mostly prepared and produced by the prime contractor, which is Surrey Satellite Technology, SSTL, and also with a lot of contributions from the rest of the science team. And this team is La Sapienza in Italy, together with IFAC and Tor Vergata University, also in Italy. We also have as partners the Finnish Meteorological Institute in Finland, and in the UK, the National Oceanography Centre and the University of Nottingham. First of all, I will explain very briefly this new program. It's a new program at ESA. It's called the SCOUT program. And then I'll move to HydroGNSS mission, its scientific objectives and the relevance of these objectives, and how to achieve these objectives, which is through the GNSS reflectometry technique. So I will also very, very briefly explain the technique. Then a mission overview and our role in this mission. The ESA Scout program is a new initiative from the Earth Observation Directorate. It's meant for small satellite missions to demonstrate science with a small budget and rapid turnout. I'm trying. Okay. The missions are fully funded by ESA. That's a good thing. Are characterized by an agile and low-cost development. And the idea is to prove new concepts for future missions. The difficulties or the challenges, as you can imagine, the schedule, it must be launched within 36 months after the kickoff, and the budget is below 30 million. The data must be open and used and delivered through service-based approach. And we participated in the first call that was in May 2019. 4 candidates were down selected for consolidation studies. So there were 4 consolidation studies for 4 different missions. And finally, 2 of them were selected for implementation. The first one to be selected in December 2020 was the Earth system processes monitored in atmosphere by a constellation of CubeSats. And the second one, a few months later, in February 21, was our mission, HydroGNSS. In a nutshell, the HydroGNSS mission, as I said, it was selected in February 21, becoming the second ESA Scout mission. And we address what is called essential climate variables, ECVs, as defined by the Global Climate Observing System. The ECVs that we aim to monitor are soil moisture, biomass, and permafrost. And we also want to monitor inundations, especially for wetlands, as wetlands are the primary source of greenhouse gases, and these are also an ECV. To monitor these variables, we are going to employ the GNSS reflectometry technique that I will explain later. And this is novel, complementary, and a unique sensing technique. The scientific objectives, as I said, address a few essential climate variables, and these are defined as physical, chemical, or biological variables that critically contribute to the characterization of the Earth climates. And we are going to monitor 4 of them that are circled here. And as I said, using reflectometry to deliver new satellite observations that are sensitive to these climate change indicators. Soil moisture contributes towards the Earth weather forecast, also to climate predictions and agriculture. Biomass, it's a CO2 or carbon dioxide source and a sink. And also it's a water and energy exchange with the atmosphere. A difficult parameter is the permafrost, the upper layer, the freeze and thaw status of the active layer of the permafrost. This is also a carbon dioxide source and sink place, and with large potential for methane source as it thaws. And we are particularly interested in inundation and wetlands. I will explain this also in a bit more detail later. And there will be a set of secondary products over the ocean and on the cryosphere, like ocean winds, the sea ice extent, the melt, the sea ice type, thickness, and so on. This mission is relevant because it monitors several aspects of the water and the water cycle. And as we know, it's a natural resource. It's vital to climate, weather, and also life on Earth. It's present on or in land in the form of soil moisture, wetlands and rivers, snow and ice and vegetation. Now I'm going to give a bit more details of these 4 variables we want to monitor, like soil moisture. Soil moisture is important in agriculture, but also for flood awareness systems. It's in climate-related studies. It's also important as a land atmosphere feedback processes. It plays a major role in separating the precipitation water, what part goes into runoff, in subsurface flow, and also in infiltration. So for hydrology, for flooding awareness, as I said. And as I said, also the feedback between the climate and vegetation, it's an important part. On one side, the climate and the vegetation have influence from the soil moisture and the other way around. So it's a full cycle process. Permafrost, this is of interest, as we can see in the picture, for some civilian aspects. In the northern lands, most of the infrastructure and buildings are built on permafrost, and as this is now melting or thawing, it might pose some dangers, as we can see in this picture. But it's also important for other studies, other scientific studies. Again, for climate, it stores carbon-based remains of the plants and animals that were frozen before they could decompose. And scientists estimate that the permafrost holds almost double the amount of carbon that is currently in the atmosphere, and this could be released as the permafrost thaws, melts. It's been also, it's not mentioned here in the slide, but apparently there are some old virus, I think, that are also trapped in the permafrost. And it's probably, I think they are studying what might happen with this virus, and yeah, when it melts. A biomass, or the above ground biomass, it's important for the carbon dioxide. It withdraws it from the atmosphere and stores the carbon in vegetation. And this process is comparable to the amount that actually stays in the atmosphere. These vegetation systems have the potential to either take more carbon in the future or to contribute to the atmospheric carbon as a large source of carbon dioxide. So depending on the quantity of biomass, the vegetation cover can have a direct influence on this local also and also global climate, particularly on air temperature and water vapor. Wetlands, in terms of climate, are important because of the link they have with the methane gas. And the methane, the global warming potential of this gas is estimated to be between 28 and 34 times higher than the carbon dioxide. Unfortunately, the amount of methane in the atmosphere is much lower than carbon dioxide. And wetlands are the largest natural source of this atmospheric methane. And it's not well monitored. It is estimated that by the end of this century, these natural methane emissions from wetlands could increase up to 80% compared to the beginning of the century due to climate change processes. The rising the temperatures, higher water tables, the thawing of the permafrost that might create new wetlands. So all these contribute to the swamps and the marshes and bogs, so different types of wetlands, to release more methane into the atmosphere. And HydroGNSS is also relevant to the models. The models needed for understanding these processes and also to predict, like the numerical weather prediction for the weather forecast, but also the Earth system models are more complex models that do not only account for the weather system, but also for all the other Earth systems in an interactive way. And we want to measure all this through the reflectometry technique. This is a biostatic radar concept that uses opportunity signals. So signals that were not designed, are not transmitted for Earth observation. In this case, the opportunity signals are the signals transmitted by the navigation satellites. These signals bounce off the Earth's surface, and then they are collected by a dedicated receiver. I hope you can see my mouse. So that would be the signals coming from the navigation satellites bouncing off the Earth and then collected from a dedicated receiver. The received power that takes this kind of shape has contributions at different Doppler frequencies and different delays, what we call the delay Doppler map. If this is the surface and this is the specular point, the surface around the specular point has different Doppler values according to the velocity of the transmitter and especially the receiver, and it also has different delays. And depending on the scattering process, the surface conditions, the receiver collects power from different delay and Doppler cells, and that maps into these kind of shapes, the delay and Doppler map of the power, the collected power. And looking at these delay Doppler maps, the power level and the spread and the shape, we can extract, infer information about the surface properties. So that's the principle. This technique is unique in the sense that is one of the few techniques that use the forward scatter geometry, and this gives stronger echoes and finer resolution over smooth surfaces, while, for instance, backscattering geometry is the opposite. It works at L-band, that means approximately 20 centimeters electromagnetic wavelength. It's microwave signals. This offers deeper penetration into the soil, the vegetation, and the snow that most of the higher frequency active systems. It has the ability to sense water and the vegetation and the even very dense vegetation canopies. And as we can use multiple satellite transmitting navigation signals, it means that this is not only a bistatic radar, but we can call it a multistatic radar. And this can be done without a transmitting system in our sensor, because we use the navigation satellite transmitters. And that also means that it can be implemented in very small satellites, in fact, even in very small CubeSats. It's a low mass, low cost approach to L-band sensing, so it's suitable for constellations of small satellites. And that gives extra coverage, extra spatiotemporal resolution. It's also complementary to other missions. It complements other missions at L-band, like SMOS and SMAP. These satellites have been very powerful, but they are at the end of their life with no immediate successors. It also complements the Earth Explorer, the ESA Earth Explorer biomass satellite. For instance, biomass satellite, which is, as you can imagine, a satellite intended for biomass measurements, cannot operate at high latitudes. And in this case, HydroGNSS will cover this gap. It also complements other C-band radars like ASCAT and Sentinel-1. C-band are higher frequency band radars, so the sensitivities are different. And it also covers gaps, temporal gaps, before the new Copernicus missions at L-band that will measure similar measurements like ROSE-L and SIMR, that they should be launched between 26, 28, no earlier than 26 in any case. HydroGNSS will be based on very well-established reflectometry approaches, approaches that have been implemented in past missions and current missions, like the UK TDS-1 mission and the Cygnus NASA mission. And this approach is the delay Doppler maps incoherently averaged for GPS signals at one frequency, which is the L1 frequency, and with sampling rates between between 1 and 2 hertz. The novelties of HydroGNSS is that we will collect signals also from Galileo, not only GPS. This will increase the coverage, and it also have longer codes for increased coherent gain. This is a technical aspect, but can be an important issue. Another novelty of this mission is the polarization. For the first time in a space, there will be both polarizations active, meaning that we will be collecting left and right-hand circularizely polarized signals. And we estimate that this is a good thing to help separating the soil moisture from the roughness and vegetation effects because of the polarization aspects of the scattering. Another novelty, and this affects us as IEEC very much, is what we have called the coherent complex channeled. That means that we will be collecting not only power DDMs at 2 hertz, but also very high sampling rate data, probably 250 megahertz sampling in phase and amplitudes, but only in 1 pixel, the peak pixel. This will be something quite new, and we estimate that it will be very useful for improved resolution, but also to help characterizing when is the coherent scattering, and that's useful to distinguish between wetlands and other not saturated lands. There we also have a second frequency, L5E5, and that's also good for higher resolution. And in this plot, we've tried to map graphically the difference between what we had in the past with that was GPS L1 power waveforms in just one polarization, and what we'll have now with HydroGNSS. And despite in the past for TDS1 and Cygnus, we only had these DDMs, power DDMs at one frequency from only GPS and one polarization. It's already been proved that there is sensitivity to soil moisture. And in fact, this sensitivity to soil moisture is comparable to monostatic SARS. The potential resolution has also been demonstrated to be between 2 and 7 kilometers. And this can be even better when the scattering becomes more and more coherent. The reflectometry soil moisture product at low latitudes was developed from Cygnus NASA, the NASA Cygnus mission. And now we need to cover the higher latitude. And the dual polarization, this is something new, as I said, has not been demonstrated from space, but in principle should help separating these moisture effects from the roughness and vegetation effects. And here what we see in this plot are results from a dedicated mission, the soil moisture mission from NASA. It's this big satellite. The antenna diameter is 6 meters. Here we see some variability in the soil moisture estimate from a SMAP in Australia. And here we have the Cygnus, the GNSS reflectometry from the Cygnus mission. The increase or the difference in the signal to noise ratio also for the same period. And we can see that they correlate pretty well. This is done in this small satellite, the constellation of Cygnus mission, reflectometry missions. The size of the satellite is 1 order of magnitude less than the diameter of the antenna. And of course, the antenna is even smaller than that. For wetlands and inundation flag, as I said before, this bistatic forward scattering geometry, it's stronger over flooded areas when they are flat and smooth. And for instance, even if the L-band signals can penetrate through the vegetation, the fact that we use the forward scattering instead of the back scattering or the emissivity, the radiometric measurement, makes that we can get these maps with much more detail and much more penetration. What we see in these plots on the top is this as map passive, so radiometric measurements over the Amazon basin. We can see here the low resolution of these kind of measurements. Then SMAP also had for a while a radar at L-band. All this is L-band, like the GNSS-R measurements. But we can see that the penetration is not as thick as, for instance, the information from the radiometer and the information from the GNSS-R, which is that on the bottom. The resolution and penetration is much better in that case for the reflectometry instrument. And also, as we will have the coherent channel, this will increase the resolution, and it also may allow the water detection with weaker signals, higher spatial sampling, and potentially we have to demonstrate, but maybe the river width and the lake altimetry measurements too. For biomass, in general, the vegetation attenuates the soil specular reflection due to the absorption and the scattering through the vegetation canopy. The sensitivity of the signals with respect to the above ground biomass does not saturate for L-band backscattering. But GNSS reflectometry is forward scattered, so we have to prove this. With the novel coherent channel and the polarization capabilities, we hope that the separation between the soil moisture and these roughness and vegetation effects will be better, and also the gain will be also increased. Even though using Cygnus data, that means only the single polarization and the old-fashioned reflectometry type of measurements, we can see here how it compares the Cygnus above ground biomass measurements in this column, how they compare to the geocarbon, which is a database for above ground biomass. This is for the Congo area in Africa. This is for the Amazon basin in America, and that's for the southeast of the US. And finally, for the permafrost, this has also been proven very recently. We could demonstrate that this reflectometry reflection power diminishes when the soil surface is frozen because of the permittivity of the frozen soil. And what we can see in this plot is the reflectivity of different pixels around the North Pole, the high latitudes in the North Pole, in monthly means. And blue is for frozen soil and black is for melted or thaw pixels. And we can see this evolution with time. With these measurements, we can feel a gap between the end of life of two L-band missions that were devoted to similar products, especially soil moisture, like SMOS and SMAP, and before the new missions, the new Copernicus missions that can continue these measurements are launched, like SIMR. And it's important to remark, to highlight that these past missions and the future missions are much bigger in terms of mass and also in terms of cost. We can see here almost 700 kilograms for SMOS, almost 1 ton for SMAP, more than 300 million euros in 2009 of cost, and $1 billion for the NASA SMAP, while we have to survive with less than 30 million and just 40 kilograms, right? Similar numbers as in SMOS for the SIMR. And the general plan, we just kicked off in August. That was the kickoff of the implementation of the satellites. We are now approaching the preliminary design review in April, expected for April. Approximately in 1 year time, we'll need to go through the critical design review, and the launch will be around mid-2024. And now I'll try to show a video. Let's see if it's running. It's a summary of this mission prepared by SSTL. This is the HydroGNSS satellite. The size is like an oven where you bake, so it's pretty small. And using reflectometry, we'll sense permafrost, biomass, the soil moisture, and wetlands, as I've just presented in the slides. And here we can see the constellation of GPS and Galileo transmitters. And we use these transmitters. They bounce off the Earth, and then they are collected by the HydroGNSS satellite. Each of these points is one of the specular points where we measure. So the yellow tracks is the measurement tracks. And these are the DDMs, the measurements, the power measured through at each of these specular points. And these measurements go through different surfaces to measure, as we said, the soil moisture, the wetlands, the biomass, and also the permafrost. There are also secondary products like the sea ice extent and the ocean winds. And here we can see with two satellites, which is our target. We would like to launch 2 satellites. ESA has approved one of them, and SSTL is now funding, trying to find funding for the second one. And in 15 days, we would have global coverage. And this is it. So now we can go back to the presentation. And with that, and to finish this presentation, just to explain what is our role in this mission. The Earth Observation Group at the Institute of Space Sciences, we are responsible of some modules of the end-to-end simulator, in particular some instrumental aspects, the modeling of the covariance of the observations and the generation of noisy realizations of the delayed Doppler maps. We are also in charge of the orbital module to simulate the orbits, and the coherent channel simulator. This is, as I said, this high sampling rate complex, so amplitude and phase observations across the land surfaces. That's quite challenging, and we'll start very soon to work on this module. We are also in charge of the level 2 operational processor for the surface inundation flag, what is useful for the wetlands and floodings in general. And for that, we'll need to use both the standard 1 Hertz power DDMs and the new high sampling rate complex observations. We also have to deliver a software receiver to process in lab, so ground-based processing of some short streams of data that is not processed at all on the satellite, and it's downloaded to the Earth as very raw data sets, and it needs to go through a software receiver to obtain the observables. And that's another piece of software that we'll be delivering. And also I'm co-chairing the science advisory group of the SAC, and this is our contribution to this mission. So to conclude, final remarks, the soil moisture and other hydrological variables are highly relevant, and they remain not properly measured, especially at high latitudes. This mission, the HydroGNSS mission, targets 4 ECV-related parameters: soil moisture, inundation, the permafrost, active layer status, and the biomass. It's based on well-established and also some new observables. The new are high rate complex channel, the dual polarization aspects, Galileo measurements, and also dual frequency. L5 will be new also from space. It will be 1 or 2 small oven size GNSS reflectometry satellites, 40 kilograms each. It's a low risk but high rewards with different first of a kind new GNSSR measurements observations. The phase, the B phase or implementation of the mission kicked off in August 21, and it will be launched in second half of 24. It's a low-cost route towards unprecedented temporal and long-term continuity if we can follow this mission with a constellation. And I think this is all I wanted to explain. So thank you for being here. And now I'm going to stop sharing my screen.
Okay, thank you very much, Estel. Very nice presentation. So are there questions for Estel? So please either raise your hand or unmute yourself and go ahead and ask the question.
No questions.
No questions? I have one question, maybe. It's related to the second satellite. So it depends on this company in getting funding for the second satellite. But you said in one of the slides that the budget allowed for 2 satellites already. So what was
Yes,
the
the
problem?
budget as we presented to ESA, so our proposal to ESA was to make 2 satellites within this budget. But ESA preferred to be more conservative, and it considered that with this budget we should do only 1. So now the funding for the second one must be found. But in any case, the cost of a second unit is always much lower because there is no development. It's just replicating what it's done for the first one.
Would they go in the same launch or it's 2 separate launches?
Well, it all depends. I think it will depend on... I'm not sure about this because on one side there's a technical aspect, whether it fits, 2 of them would fit in a launch. The launch must be an opportunistic launch, so it will not be a dedicated launch. So it will be a launch of probably another bigger satellite, and if there is a space for 2 HydroGNSS, I understand that it would be possible, but I'm not sure about that. And the other constraint is the time. If the funding is found too late, maybe there will be no time to have both satellites ready by 24.
I see Daniele has a question.
Yeah, very, very nice talk, Estel. It's related to this, I don't know if you mentioned it, but about the constellation that you mentioned at the end, is there already any plan of how many units there will be?
No, there are no plans. In fact, we are still looking for funding for the second unit. I think the idea is that this scout mission, the intention or the goal of the scout mission is a sort of demonstration. And then if successful and useful, these satellites pave the way towards a constellation. So I think that if HydroGNSS is successful and it's proven needed or required for the future, then ESA or other agencies might consider to deploy a constellation of HydroGNSS.
Thank you.
Okay, Giuseppe, go ahead.
Yeah, hello. Nice presentation, Estel, thank you. Maybe I missed this information, and sorry if I'm asking something that you already explained, but could you tell us the duration of the mission and how this is related with the altitude of the expected orbit?
Yes, the mission, wow, I don't remember. 3 years as nominal lifetime, maybe? Maybe it's in the, let me check the slides because maybe it's in the planning. No, it's not in the planning. Sorry, I don't remember for how long it will be orbiting. What was the second question? The altitudes.
The altitude, because I guess it constrains the duration of the mission. I was wondering what was the altitude and how this is connected to the duration. But I can.
Yes, the altitude around 600. Weishan, are you connected? You did the last, we are still through the simulation phase for the design phase. And recently Weishan did some simulations, orbital simulations. If you are online, Weishan,
yes, I'm here.
The simulations, at which altitude were they made?
It's 550 kilometers.
550, okay, yeah. So almost 600, yeah.
Okay, thank you.